Okay, streaming and recording seems to be working. Okay, I think I probably for the best if I provide the link in Zulip. How do I find the link again? It's very frustrating that YouTube doesn't just like show you what the link is on the main screen. Okay, so if I open this, if I go to YouTube and I click on my studio here, perhaps. I guess the appropriate name here. The appropriate name is this is date. Oh no, this is a fine. No, this title is fine. Yeah. How do I? Right. How do I find the link? My channel clearly. Okay, this is it. Here's the link. Link here. Anyone has no YouTube account, all free to start another thread, or to link to another thread from here. Give comments on Zulip. All right, there we go. Okay, progress is being made. And also probably better if I make sure that I can see everything, so I won't get my windows organized. Yeah, that seems fine. And it can hear me as well. Great. Okay, so what to do today? Where was I yesterday? No one, do I even remember? So I'm in the middle of proving this theorem. The least common multiple of the first n natural numbers is at least to the power n for all n greater than 7. And we're doing this using this proof that uses the beta integral, which is this integral here, the integral from 0 to 1 of x to the something times 1 minus x to the something. And there's two different ways that you can evaluate this integral that give you two sort of different equations, and it lets you know basically that, so basically the critical fact is this: m times n choose n, or m times n choose m divides this LCM thing. And this is this critical fact that you can use in a few ways to like prove the theorem. So basically that's what I'm trying to do here. So basically I re-expressed this in a form which is a bit more amenable to what I'm trying to do. But yeah, so we have this, and the point is that you should be able to use this to prove that using like these two facts. So I was making progress. I was currently on, well, in previous episodes, I was, having trouble with random things, and I thought, today I might try and use AI to see if that's possible of resolving them. Let's see, what was the key one? Let me see. Yeah, it was like this one. So this was some theorem, and I thought, oh, this theorem should be pretty straightforward, but the automation techniques weren't being able to solve it. Like grind failed, and probably ASOP would also fail. Yeah. But it should be pretty straightforward. The point is that x is this positive number, positive integer, I guess, being cast to a rational here. But the fact that, okay, so it's positive, and so we know it's greater than 1, and we know that it's less than b because it's positive and it's less than b. So this shouldn't be too hard to prove. And my thought is, okay, well, what if I just like boot up the chat mode and see if it can prove this? So what if I say something like, please prove the sorry on line 164. And it will work. I'm trying to figure something out. Need to examine the context. Right, okay, so this is where I start granting permissions to it willy-nilly. Right, this is like an MPC servers, yeah, so this is like very insecure probably. So it's like sort of a catch-22 where if you grant these permissions, you like get in the habit of granting these permissions, and it's probably like pretty bad for your computer security. But I think that for today, I will allow in session. So I will allow it for today. Can see the context. Yeah, so that's the thing you're proving. And you want to be able to, yeah, so you want to be able to like see goals. So I'm going to allow you to see the goals. Yeah, lean LSP MCP server. So I guess this is something provided by the lean, by the lean VS Code extension. Yeah, what happens if I click this, by the way? Servers, lean LSP. Is this something I installed myself? I don't really know, unfortunately. But okay, so I was thinking, examine what needs to be proven there. So it shouldn't take too. So this is what needs to be proven. And I would hope that it wouldn't take too long to produce this proof or to like understand what's going on, but it seems to be thinking about it for a while. Yeah, so this is the other sort of like critical fact, which I guess I need to prove by induction. This is sort of like another thing that I noticed, which is like using natural numbers. There's sort of a convention to use natural numbers rather than the positive natural numbers. There's a type for the positive natural numbers, but no one ever uses it. They always just use this. And I sort of wonder what the ecosystem would look like if it were just much more in favor of using like the positive natural numbers. Because for example, this thing that I was doing yesterday, yeah, so like a large part of yesterday or the day before, whenever I was doing this last, um, was me like just writing this variant of the binomial coefficient function, yeah, which returns a positive natural number. And so I could have asked it to like return a positive natural number probably. And it would be interesting because positive natural numbers, their divisibility properties. Positive natural numbers have unique like prime factorizations, which is not exactly the case for natural numbers with zero, right? Because zero doesn't have like a prime factorization, I guess. And so like you could imagine that like if we had like a whole like plethora of theorems about p nats, which are just like variants of the existing theorems that we have about nats. Like one imagines that one could get like more efficient proofs in some cases, yeah, at the cost of like tons of API. Okay, let's see what's going on. It's still thinking. This is sort of strange. Here, let me go like look at the so lean LSP. So I sort of assume that this is lean 4, right? Does this say that it has the lean 4 VS Code extension manual? Okay, can I see this manual? Yeah, I'm just going to open it in another window here, but why don't I open it over here to like read what's going on? I'm going to interact with the most recent version. Does it say anything about MCP? Find MCP. Apparently not. Yeah, so what is providing the ability of it to do this? Okay, like second question. If I like just search the thing itself for MCP, is there any mention of MCP? Yeah, that's sort of weird. Okay, so maybe it's not here. Do I have anything? Yeah, this doesn't look lean specific though. Is it something that I like installed months ago and just don't remember doing? So this is interesting. Like we can see what this provided though. So we ran lean file contents. This seems like incredibly simple, right? All that it's done here is it's like dumped the entire like contents of the file. Annotate lines of true because I asked, right? Because clearly I asked line 164, and so the model was smart enough to know that it required a readout of the file with lines annotated by number. And so it did that, and so it was able to like see the context, yeah, and then it started doing this. But of course, okay, lean goal, line 164. Okay, so this is what I want to know here. Like, Google, tell me the answer. What VS Code extension is providing my MCP? Extensions that provide MCP server support. See installed extensions, right? So if I look here, and I go for MCP, yeah, I don't know exactly what's going on here. Okay, like my computer is also going wild. Why would see that doesn't make sense? Why is my computer fan running when like I assume that this command here would be like making some sort of external call. Running lean goal. What exactly is happening here? Presumably, this is just a command that allows the LLM to see what the goal state is here, which is just this. But for whatever reason, it seems like it's not working because I would expect that to not take as much time as it's currently taking. So that seems to be some sort of issue. Here, if I go back to this, restart extensions. Why is it saying restart extensions? Okay, just a sec. I'm going to stop this. Yeah, clearly this was failing for whatever reason. What if I restart my extensions? New dev container configuration file. No, I don't think that's important. Okay, so I restarted the extensions. Did that change anything? The key thing, like I sort of want it to be able to lean LSP. Application support code user MCP servers lean LSP. So I don't know what installed this. Ugh. So I don't know, I don't even know. It feels like there's some sort of error going on here. Output canceled, yeah, because you weren't taking forever. So I don't even know necessarily what this is. This is very frustrating. What happens if I this doesn't seem to be associated with the lean4 extension though, because I don't see anything in this this readout which says so. Is it okay? Let me try and recall if I installed something. Lean for MCP. Did I install this? Lean there improver MCP. What exactly is this? Lean hammer, lean search, Lugal. Right, so install UV, and I feel like it said something about UVX. So maybe I just installed this one day a few months ago and forgot about it. Make sure your lean projects builds quickly. Yes, code setup. But actually I don't necessarily see that any recent updates have been made. I don't necessarily know if I'm going to be able to fix whatever's going wrong by updating this. Let me see. Lean goal. Get the proof goal as a specific location. Yeah, so that's what it was doing. Okay, I can always just try again, right? So here, restart file. Let's see what happens if I restart the file. Yeah, I think... Did it say that I had to rebuild the file or rebuild lake build? Make sure your lean project builds quickly by running lake build manually. Yeah, so I wonder if that was my issue. Oh, yeah, look at this. It seems to be recompiling MathLib. Oh, I have a comment. Let's see. Eq nat abs of non-neg will give you x equals x nat abs. Okay, yeah, great. That seems like it would be helpful. Of course, now I can't do it because it's reinstalling everything. But maybe there was some issue around no, because I know that the version of the file that I had was already built because I was clicking around and seeing different things in the info view. So I don't know what the issue is there necessarily. Okay, so the key problem I have now is that MathLab is going to be reinstalling everything. And this is something that VS Code extension does not exactly do a great job dealing with when I want to just get the cache. Like here I am building the file. I want to simply get the cache, right? So I should fetch MathLab build cache. I'm in MathLab, right? So I should be able to run this. And what exactly happens? So clearly this number has stopped going up, I think. This is a great way to get yourself. Yeah, target is out of date and needs to be rebuilt. Does this, okay, have I successfully downloaded the cache? Okay, no, now I'm back to 1300 or whatever, or 13, yeah. So apparently this is not something that I have successfully been able to do. This is, yeah, it's very annoying. I just want to, it should not be too hard to get the, okay, so now I have to go away from my AI explorations at the moment and try and fix this stuff that's going wrong where I am rebuilding MathLab. So I just want a quick way of getting the cache, right, without, it just doesn't work when I get the cache, right? And there needs to be more explanation about what I'm supposed to do, like lake xc cache get. This is probably the problem is if I do this when I'm building, it's not exactly clear what happens. There should be some sort of warning. Yeah, no files to download, completed successfully. Okay, stop. Just, how do I stop server, stop for server, stop server. Okay, my computer still seems to be consuming lots of power though. So I'm like not totally sure that I've stopped it. What happens if I kill lean? Okay, no, that's not going to be possible because I have like 16 lean threads running. Okay, that's annoying. Okay, what happens if I delete my VS Code window? If this managed to cause it to realize it should not have any lean processes running anymore? I just killed my VS Code window. Why are there still lean processes running? Is the issue that I have another lean process open somewhere? Here, let me like close my other windows. Cancel. Yes. I just delete that. Do I have anything else? What is this? Yeah, this is something I can delete as well. All right, so let me try and reopen MATLAB. Yes, like dozens and dozens of lean processes running. And I don't want that. And also like lots of lake processes running as well. I'm not exactly sure like how to like get my computer out of this state when like there's no reason. Here, let me close this again, right? Visual Studio Code. There should be no reason for me to have a bunch of lean processes running, but my activity monitor tells me that I do. So what happens if I start like quitting them? Quit. Kill these lean processes. It's literally like there's like a virus infecting my computer, like making tons of lean processes. Maybe I shouldn't have allowed like this MCP server to, yes, quit, lean terminated. It's like they're, okay. Maybe a lake is the one I have to kill. Let me like try and force quit this lake process. Why would lake? The point is that lake is probably making a bunch of other things. Okay. So there's still, like quit lake, force quit lake, 3 separate lake processes running. And if I try and kill this one too, force quit. Okay, great. That seems to have reduced. Okay, finally my computer has stopped running lean processes. Okay, so what can I do to, here's like, here, let me try to make a new window in my terminal. And okay, all right, so if I cd into MATLAB, so now I'm here and I want to just do this from the command line. Lake clean. Is that a command? I want to like try to start from a fresh slate as much as possible. Okay, so now lake exe cache get. See if this manages to get my cache. Okay, completed successfully. Decompressing 7,000 files, completed successfully. Okay, so now I'm here and now I should be able to like run link build, I assume. And it should build, it should build my project. Build completed successfully. Okay, so now what happens if I do VS Code, or sorry, I think it's code, and I open the directory in code. Okay, so now I'm here in VS Code, and just to clarify, lake build says that I've already built lake. Yeah, great. It's a little weird that it like has these other things in it, but okay. And so now if I look in this file, this starts up. And my hope is that it will soon realize that, yeah, okay, wonderful. So things have all built. All right, now I got a suggestion of what I should use, but I also wanted to see if the machine would get it for me here, like at the risk of like borking my system again. I wonder what happens if I just rerun the chat. Oh, is this interesting? This is like a different icon. Did I like update VS Code? Maybe what just happened is that I updated VS Code. This icon is different than it was before. Okay, so yeah, it's on line 164. What happens if I just do this? Yeah, so I will allow it to read the lean file contents, examine the specific sorry. Yeah, and so now what it wants to do is it wants to see the sorry on line 164. So I'll allow that. I wonder if this gets the goal state before or after the tactical line 164. Okay, so it succeeded. So it succeeded and it got the output. Wonderful. So I don't know what was going wrong before, but oh, it actually gives both before and after. That's interesting. So clearly it's a sorry, so after there are no goals. Okay, so what does it want permission for now? I can see the goal is to prove x.natabs is less than or equal to b. Examine the context. Lean diagnostic messages. Yeah, okay, great, sure. You just want to see the error messages. So I will allow in this session. Yep, Yeah, when cast irrationals. Yeah, this is sort of interesting, right? This is one of those things where like the lean info view is not that great because the lean info view always renders these casts as like the upward arrow, but that doesn't tell you what type you've cast to. And so when the model only sees that there is a cast, there's a potential for it to get confused about what it's being cast to. Um, Get hover info. Okay, you want to be able to like hover over things. Okay, cool. Allow. Like it wants to hover over. Yeah, so it just wants to hover over a specific location. Interesting. Yeah. Well, you hovered over some. You got a bunch of different information. Very useful. Get the proof state. Yeah. Okay. So I'll allow this. And okay, this is get the proof goals. Did I not already give permission for this? Mean goal. Maybe I need to allow in this session, rather than just allow as a one-off. From this, we can deduce that x is greater than 0. Then use int, wonderful, int.natabs of non-neg. This is exactly what Assembly Wizard in the chat suggested. So clearly both Assembly Wizard and Claude Sonnet 4 are more knowledgeable about the space of MATLAB declarations than I, but happily I have their assistance in making this. Search for documentation on int natabs of non-neg, right? I didn't actually provide int natabs of non-neg, right? It just it figured out that was what was presumably needed. Okay, so now it's like, of course, now it's figured that out, but it's experiencing a bunch of errors because it is hallucinating declarations, apparently. Failed to find a contradiction. This is a little surprising. Why does it, x is, yeah, well, this is not true. So I don't know why it's, well, wait. No, yeah, this is true. Why does Linarith fail here? We have one. Okay, the thing is, it's like it changes, it like tries again and tries again. It's just like throwing random things at the wall until something works. Yeah, rewrite failed. Did not find the occurrence. Like probably if I just paused it at some point, I could like go in and figure out exactly what was wrong. Oh, it wants get code completions. Sure. So this will presumably allow it to like see what the fuzzy finder would give it. We approach this more systematically and use a different strategy. And it always says like, yes, I will use an even simpler approach, and that will be even better. Yes, natabz equals natabs of non-neg. See, it's very surprising that omega could not prove this goal. I guess the issue is that these are rationals and these are integers. B is an integer. See, it was very close right there. I sort of wonder if the art is just like looking at the art to using this. It just like tries things again and again, and it never gets it perfectly right. I don't know what the best way to do it is. Like maybe to now it's exploring monotone class. Like the best way is just to like stop it when it gets something that looks like it's very close to correct, and then correct it manually. No goals to be solved. Okay, surely this is great, right? Okay, so stop. You said no goals to be solved. When the issue is no goals to be solved, I can just comment it out, and that should be correct. Okay, great, check. Wonderful. Okay, so we have a proof complete with like tons of inline comments. All right. Well, it basically almost got there, but the key thing is that it knew the name of this lemma that I would otherwise have had to look up myself or rely on YouTube to figure out for me. All right. Okay. So what should I do with the rest of what I want to do today? I might want to. Okay. So yeah. So that apparently was accomplished. And probably it would be better if it were like severely golfed from what it is now. Like for one thing, I don't necessarily want all these inline comments. So I'm going to delete those. So what do I want to do next? So I could prove this theorem. I wonder like what would happen if I tried to get it to prove this theorem. Because it clearly sees the definition here, and presumably it can do some sort of induction. So let me try and ask that. Like, okay, now prove the sorry on line 137. Okay, let's see. Let's see if it asks again to see like the readout of the read LCM lower bound 130 to 145. Yeah, so it reads like a portion of the file, I guess, just to like get the quote unquote context. Examine the definition of LCM to understand how it's constructed. Yeah. LCM n is the LCM of all numbers from 1 to n. I need to prove this by induction on B. Let me implement the proof. Yeah, okay, so induction on B. Yeah, see, the thing is, I think you will actually need to do induction on B where you do 0 as a separate case. Using LE induction. I don't know. Sorry, let me look up LE induction. Oh, it changed too quickly. Oh well, yeah, this is like hilarious, the experience of coding where you have to like click quickly to like understand what the AI is doing before it moves on to something else. Okay, and that's strong induction on. This seems a little more likely to be successful. If B equals 0, then A is less than 0, which is impossible, and we managed to prove that. Otherwise, case B is B plus 1. Yeah, intro and fill. There are no additional binders or let bindings. I don't know why it's trying that. Yeah. Still an unsolved goal. Okay. Here. I'm gonna stop this and like give it a little bit more guidance because this is just ridiculous. So the point is that we want to do like cases on B, right? So cases B with 0. Sorry. And this should be, and then when we do this, now we should do induction with 0, submit something, rewrite something, sorry, and then we should do this and have a sorry here. Okay, so now my instructions are, I wonder if it's better to like, okay, wait, if I start a new chat, probably I have to re-grant all the permissions, so I'm just gonna keep with what I'm going here. So please prove all the sorries from lines 139 to 148. Like in theory, this should probably just be like omega or something, like rewrite LCM symbol. So we'll see if it manages to do that. I mean, like one thing that would be a useful skill for the AI to have is to work on one sorry, figure out when it's like successfully finished it, and then move on to the next one. None of this should like impact A is less than 1. Yeah, 1 is less than A is less than 1, A is equal to 1, phi A is equal to 1, literith, basically. And then this is the only like advanced case, right? So this would be another rewrite LCM. Is this even like technically right? This is like, I'm noticing now that my like definition of LCM, so it can either be 0, 1, or n plus 1. But of course, 1 is already of the form n plus 1, so the point is that this is how you do it if it's n plus 1 plus 1. Okay. It successfully read the file, and now it's running lean goal. Ran lean goal. So it got the goal on line 139. Great. So the question is it going to, okay, so did it check all, is it checking all of them? Line 145. Yeah. So it has a good summary. Like he knows all of the sorries that it needs to do. Yeah, this is literith. I think it should realize that has been successful. Okay, yeah, no goals. So this one, the thing that it needs to do, yeah, maybe the issue, 1 less than A is lesser. Okay, so clearly the issue here is just that we have a contradiction in the bounds. Okay, so it made some progress. What happened here? Yeah, so we did induction B, and it successfully proved this one, right? So now it's trying to proceed to prove the hard case. Really, it should rewrite LCM, yeah, and what it should do now is it should say that no goals to be solved, or no additional. Okay, so clearly it screwed up. What actually, like the point is that the proof here should look something like apply LCM, apply the definition of LCM, then you have an LCM, and then you have A divides that or that. Yeah, so it shouldn't be too hard. Okay, just a second. Did it like, okay, now it's like deleting a whole ton of stuff. Okay, this is horrible. It undid the progress it made, did it not? Induction B with, okay, I'm gonna, why is it's changed it to not use the cases anymore, which is not what I wanted it to do. Okay, I'm gonna stop this and undo. Yes, I would like to undo. Okay, so I'm just gonna prove this manually because this should be pretty trivial, right? Like grind, and this one should also be probably grind. Yeah, and this one is not grind, but if I rewrite LCM, then I have this. And what I want to do here is I want to say A divides the least common multiple, if and only if A divides this or that. Rewrite LCM divid. I would think it would be divid LCM, right? Divid LCM. Okay, what am I trying to, is there an actual theorem here? Let me think through this. If A divides the LCM of B and C, then A divides, no, you could have like 6, 2, and 3. So that's not something. So the actual logic is that either A is equal to B plus 1 plus 1, in which case it divides the LCM for the left reason. Otherwise, it divides this, and it's true for the right reason. So by cases, yeah, that's what we want. So these are two, sorry 1, sorry 2. Can I like grind these out maybe? No, exact. So if A, okay, number 1, it should be like the same form, subst H exact. Yeah, okay, and so it knows that it's the left. Otherwise, we have that, yeah, and who knows what the rest of this proof is, but the point is that we specialize the inductive hypothesis with this too, the inductive hypothesis with this is all I really want to do. A divides this, and now it should just be an exact, right? An exact question mark. Why does that not work? A divides LCM of B plus 1. But here, we did divid LCM left. So can we not like apply divid LCM right? What's the issue? Yeah, let me think about this. The problem is that it's not equal to it. It's something that divides it. So this is not the right thing. Sorry, just to like refresh. If A divides N, then A divides the least common multiple of M and N. I guess there's like a non-zeroness requirement there or something. I'm not seeing an answer there necessarily. This big grind, why does this not work? The point is that here in this branch, I have A is not equal to B plus 1 plus 1. We also know that A is less than, so we should have that A, why does this not work? This is a little strange to me. Okay. Yeah, that makes sense. And the thing we have to do here is use the fact that this is non-zero. This doesn't work. I feel like there should be like divid LCM of divid. So let's try and look for that on Google. What I'm looking for is something that says that if something divides something, then something divides a nat.lcm of something and something else. And so it gets these ones, and it's this. That's so close. So just to clarify, it should be like this, right? And also, I don't get what's happening with 0 here. A divides B, C. A, B, LCM, C. Okay, so just a second. So A divides B is in the hypotheses here. So A is A, and B is LCM B plus 1, and C is this. So shouldn't it just be this? Nat dot divid LCM of divid right. Non-constant. Data nat. Okay. Am I importing all of MATLAB here? Unknown constant. Okay. Is this a case of some theorem not being added, or being added recently, such that it's not like visible? Okay, let me just. Sorry, where am I? Divid of LCM left divid. Here we go. Yeah. Okay. Can I go like to the source? MATLAB data nat GCD basic. MATLAB data nat GCD basic. When did this? Okay, changed history of the file. Divisibility and LCM for both GCD monoid and NAT. If I go here, yeah. Okay, the answer is that the lemmas were added in the last 4 days, and so they are not on this branch. Blizzard Inc. You may be able to just use divid trans or just the trans tactic instead. Yeah. So I guess what you're suggesting is, if I get back to where I was, it should be possible to just say something like, yeah, like trans lies to a goal whose targets trans. So I would be using like trans IH or something. Sorry, let me like read the documentation of trans. Trans applies to a goal whose target is the form this, where it's a transdifilation. Replaces the goal with two subgoals. Trans S. So what I need to say is trans this. And the first goal is an exact. And the second goal is also an exact. Yeah, yeah. Okay, wonderful. That's like a nice and clean way of doing it. Thank you for the advice, Blizzard Inc. Okay, I still have unsolved goals. What is this? Yeah, great. Yeah, I guess the point is that when I rewrite with LCM, this is something to do with the fact that I structure my induction in a weird way. But that proves that theorem at least. Following tactic starts with 2 goals and ends with 3 goals. The point is that I should not be doing this. The point is that in order to apply the LCM, I had to prove that this was not equal to 0. Yeah, I guess the point is that there should be more API around this function. Yeah, like this is like to do fix API around LCM function so that the rest of that looks nice. All right. So I feel like I'm on a kick of doing like the number theory here. So I wonder if I can like try and proceed to prove the okay, so this is like the main theorem that I was going to prove, and the point is that it's supposed to be provable from this theorem, which is this nat.choose prime theorem that I have. And so let me see if I can like prove this lemma. So the lemma, or this is the main theorem that I want to prove. Theorem LCM lower bound. Okay, looks like this is vaguely accurate. So yeah, so the way that it's proved is we invoke a couple of have statements. So we have like h binom 1, which is to basically use this exact thing that we have here. We'll choose divid LCM with, okay, so the thing that we want to use is set n equals 2m in the above lemma. Yeah, so in other words, we can set foo equal to m, and then we get, so the point is, I guess we're starting with n, so we want like n bilinear. I don't know why it's saying this, but I think it's just bilinear. And so this gets us that n times n choose prime n divides the LCM of 2n. Yeah, I guess the point is that I call it m here because I was using m in the other lemma, but the other fact, so this is slightly different. This is n and n plus 1 by Linnereth, and that gets us this other fact. So here we have n times n choose prime of n, and here we have n times n choose prime of n plus 1. Right, now maybe I want to permute these just a moment. I want to use like n plus 1 and n maybe, according to the notes that I've left myself. And so, yeah, so like how does this proof go? Let me see if I can recall. The point is that we have n plus 1 choose n, or n plus 1 choose prime n, which is, you know, in conventional notation, this would be 2n plus 1 choose n, or alternatively, 2n plus 1 choose n plus 1. And the point is that that is like a binomial coefficient that's related to the choose of 2n in this way. And so I think that like basically the point is that yeah, like so there's another way to say this, which is like this is true or equivalently. I think like another way of writing this is m plus 1 times m plus 1 choose m plus okay, m plus 1 times 2m plus 1 choose m plus 1. This is equivalent to we can like use the binomial expansion of this to write this out, right? So or equivalently, because this equals n plus 1 times 2n plus 1 factorial over n factorial, n plus 1 factorial, is this, which is really just equal to, right? So this is equal to this, the n plus 1 and the n plus 1 cancel out, and we're left with this, and we can also factor the 2n plus 1 out from this to simply get that this is equal to 2m plus 1 times 2m choose n, which is another thing of this form. So the equivalent way of writing this is like 2m plus 1 times 2m choose n divides this. And so I guess this is what we have. Maybe like rather than writing it this way, I should write it as I should write it in a way that's similar to what we have up there, which is so we already have, right? Sorry, I'm going to delete this. I'm going to comment this out so I can remember what we have. What we've just established is that it's n times n choose prime n. So the other thing we have is 2 times m plus 1, or 2 times n plus 1 times nat.choose, it's the same thing, divides this by this reasoning that I have here. And so this gets us these two divisibilities. And then, so like the rest of the argument is like this sort of slick thing where it's like, okay, we have that this divides this, and we have that this divides this. Now, n and 2 times n plus 1 are coprime numbers. Therefore, if I consider like LCM of 2n divided by n choose prime of n, right? We know that both n and 2 times n plus 1 both divide that number, and because they're coprime, their product divides that number. So the way that we continue is to say something like this works n times this. So n times 2n plus 1 times this is this. So this like follows from this, and then the point now is that we use like approximation. So we have the binomial here. Let me look up. If we go to like choose, if we go to the original choose, we have like various bounds. Like there's a pretty well-known simple bound for central binomial coefficients, which is what we have over there, which is that it's like 4 to the power n over 2n or something. If I search for 4 to the power n, I swear there's like 4 to the power n. Oh, there might be central. Yeah, so this is in this file. Yeah. So 4 to the power n is less than n times central binomial of m. So apparently this version of the bound is weaker and this version of the bound is stronger. So we could just use this version of the bound. But we have that 4n, right? Okay, so like returning back over here, the point is that like we've used the divisibility properties to get this, and I think okay, clearly the binomial is misleading, so I don't really know what I'm doing this, so I'm just going to like name this as a series of lemmas. The point is that I think what we just do next is we say h4, like, okay, this can just be written like, this can just immediately give us this. And then the point is that, okay, maybe even better would be to write it this way, which is a more suggestive way. I wonder if you can do like a calc block that has both divids and less than or equals in it. I'm not sure if that would be cool. That would be very cool if that were possible. Okay, I have another comment. Just in case, is it true that you need the 3 cases when defining the LCM function? Well, the reason I defined it the way that I did is because I'm not exactly sure. The 0 is just sort of a garbage value. It's supposed to be the LCM of the first n positive natural numbers. I suppose what could be done, is it possible to, well, that wouldn't really work. I suppose what could be done is to like shift it by -1 so that LCM of n would represent the LCM of the first n plus 1 positive natural numbers, in which case 0 would be 1, and this would be, and n plus 1 would be LCM of n. Let me think this through. So I guess the point is that we could define it. Formula work if you just skip the 1 case. Okay, so 1, in that case it would be 0, right? LCM 0. You might be right. Let's see. The point is that if I take n plus 1 to be equal to 1, then n is 0. And so we have the LCM of 1 and 1, which is just 1, which is fine. So the point is I can just delete this. And then so I don't need this additional thing here. The point is that now I can probably just do the induction directly. I think I was afraid that if I did it this way, I would be taking an LCM of 0, but clearly that's not a risk because I'm adding 1 here. So what's the best? So I wonder if I can just start the induction directly. The induction is on B here. Case is B with 0 grind. Yeah, well, I mean, I can clearly just do this, but this is not an elegant way of completing the proof. Clearly there should be one. I feel like there should be some way, if I'm going to do it this way, there should be some way of completing the proof which does not involve does not involve separately a cases statement and an induction statement. So let me try and think that through. So the question is, can I just do something like induction B with, I'm just going to comment all this out, and presumably Copilot will reconstruct it for me. 0, LCM, can't do this twice, grind, alternatives suck, keep going. Okay, I don't necessarily want that, but the point is that I should rewrite LCM. By cases now should be A is equal to B plus 1. Can this just be an exact question mark maybe? Yeah, great. And now I want to proceed with the divisibility argument. Yeah, so here what I want is that if A is not equal to B plus 1, then I have that this is true. Sorry, I don't know why that didn't, A is not equal to B plus 1. Yeah, so now I want to specialize. Now I want to use the transitivity. And why is this not proved by grind? Yeah, okay, so maybe it is. Okay, so that's a shorter proof, probably a shorter proof here. Not like counting it line by line, but I think that's good. All right, cool. Yeah, like I wonder what the best way of writing this function is. Like, is this actually a function that we want to have in MATLAB at any point? Because it's like the LCM of the first positive natural numbers. I wonder if we could just do like, I don't think that there's like a LCM for a range. Like there's not a good way of taking the LCM of a set of numbers. Or like fold, I guess you have to like fold, right? Anyway, so like I was down here. Yeah, so this is a good good way of golfing that. Okay, so here I'm going to try and return to what I was doing before. Yeah, so the point is that this is true, and we also have this central binomial coefficient, which says that 4n is less than this, right? So the point is that we also have 4n is less than central binomial n, so 4n is less than not dot choose prime of nn by sorry. And I think the point is that you should be able to like put these together, right? So therefore, 2 to the 2n plus 1, just a sec. We should have h6. So from these two, we have that 2 times n plus 1 times 4n is less than this, I don't know if that has to be strict or greater. Maybe it should just be strict. Right, and the point is that this is now like close to what we want. So the point is that, okay, so now in order to prove that this is the case, yeah, the actual point is that we should first be proving this statement for any n, and then to prove that this is true for any LCM n. So either n is even or odd. Yeah, I guess the point is just that we want like a little a lemma here, lemma bound odd LCM. And the conclusion is this, for a natural number n. The point is that we use all of this to prove that, and this is not like very judicious use of comments. But I do need n to be sufficiently large here. So we'll say gen1 less than equal to n, unsolved goals, and so this should just be sorry. But I think the point is that we should be able to use this to prove the thing that we wanted to prove, namely that, yeah, why is it 7? This is the thing that's got me a little spooked is, oh, maybe the issue is that this only holds for n greater than or equal to 4. Yeah, naturally. So this is going to be 4. And so this is presumably going to get us to like the n equals 9 case. Yeah, okay. So this is what we, yeah. So this gets us to some larger case. This is why like it turns out to be 7. We can just say something like we have all this, and so there's 2 cases. By cases, yeah. What's the like? I wonder like what is the most judicious or idiomatic way to split among the 2 cases that n is either equal to 2k plus 1 or it's equal to 2k for some k. Yeah, not totally sure. So what I'm going to do instead is I'm going to say there exists a m such that n equals 2n. This will be sorry. So in the case that this is the case, okay. So in the case that it's not the case, replace h with the assertion that there exists something of that form. Sorry. And then we proceed. Obtain, probably like obtain something. Obtain mReferral H. Yeah, that all happened. And now we apply the, what's up? I was asking if calc can compose David and Ellie. I checked and unfortunately you can't. Yeah, Ellie of David only finds lemmas for nat and pnat, ordinal and cardinal. Ellie of David, yeah. That's interesting, right? Because, yeah. I guess the issue is that 0 is a multiple of all numbers. That is, presumably that is the issue. And so it's valid to say something like 17 divides 0. And so it's not a perfectly true statement to say that, I can't just say that A divides B and B is less than C implies that A is less than C. Which is, I mean, for pnat, I feel like it would be true. But again, we don't really do that much using pnat. Yeah, interesting. Nat even or odd, is that the have H colon equals nat dot even or odd. Yeah. This one is actually even more close to the thing that I was going to use. Nat even or odd. So this, yeah, thanks. This seems like a better way of doing it than whatever I was doing before. So now I'm simply going to obtain here, and I'm going to be reduced to the case of a few different goals. Yeah, this is interesting. This is not the structure of how it should go because the exists is on the outside. So it should be something more like, is it possible to do like obtain K refl bar refl like this? Colon equals H. Yeah, this gives me the structure I want. And of course, it was not even necessary to do this probably. I could probably just do this. Yeah, so this gives me two cases, one where it's this and one where it's that. Yeah, great. Yeah, so this is, okay, so I have two cases. And I think I'm going to try and deal with the second one first because that's the one that looks more like what I have over here. So in the second case, I have some K and 2K plus 1. So the point is I want to apply transitivity. See, the interesting thing about the trans tactic is I feel like I never want to use the trans tactic. What I always want to do is yes, you included prime in your suggestion. Yeah, thank you. I'm just not good at reading comments. The thing that I want to do here is, right, so I could do trans using, and the value of S that I want to use in this case is this value. So I could do trans using this, except of course that K is the value that is of interest here. And then I reduce myself to proving this and this other thing that follows immediately from bound.lcm. But I feel like there's another way of doing this, which is just to apply LE trans. Okay, so that's like one way here. I want to like compare the character count of these two ways. So this is one way, and the other way is to apply LE trans of this. Could not unify, and like a space here. And so K is at least 3. I might have to change this to 9. I remember that it's 9 and then you like work your way down to 7. So yeah, so clearly, okay, so I guess, right, the point is that if I do it this other way, right, so one way I can do it is do this and then like create two sub-goals, and this sub-goal is by exact this. And now there's no goals to be solved. But like my suspicion is that like with this other way, I don't have to generate a side goal because it's just already inlined here. And so my sneaking suspicion is somehow that that like this will ultimately be more golfed to do it this way, even though it's not making use of the tactic because I don't have to copy out the term here, which is this sort of weird paradox. I would like, is there a way of using the trans tactic that doesn't require me to write out terms. I feel like a lot of my journey in Lean is just like trying to figure out ways of not writing terms in my proofs. If S is omitted, then a meta variable is used instead. So yeah, so I guess that there, like the other approach would be to use trans, and then like what happens if I do this? Does it? Okay, so that still works, and clearly now this is a meta variable, which is not necessarily what I want because it's always so confusing to have to work with meta variables in your code. The point is that I know it's this. Probably what I could do is I could complete the proof here and then delete this. That would work. Okay, so I guess I'll just proceed with this because in some ways this is like a nicer, even though it's less golfed, it's sort of like nicer somehow because you're sort of explaining better what you're doing. Yeah, so like to conclude here, what we have on the left-hand side is 4 to the k times 2. What we have on the right-hand side is 4 to the k times 2k plus 1. And for k sufficiently large, that is simply true. So I think what I have to do here is something like pow add, rewrite pow add, pow mul, or num, maybe like a mul, good old mul com or something. And that gets me here, and now I do linearith or something. Okay, so that's how that goes. Cool, so that's the case where it's like this. And we're like strongly close to being good. And then the other case is something like, I think in the other case, I just do something like, I use a smaller value, right? Like I think I just use the fact that LCM of 2 times k is greater than LCM of 2 times k minus 1, and it still works out. Of course, for that to work, I need to know that k is greater than 1. So that's something that I should probably establish, right? Because the point is that there's like a factor of almost k in the, does this work? Here, let me think through this a little bit more. Yeah, LCM of 2 times k. I guess we're lacking a factor of 2. So maybe that yeah, this is I think the point is that this is good enough. What we want to do is something like we want to do multiple LCMs here. So it's something like LCM 2 times k using that subtraction, k minus 1. This is not a very nice way of doing this. I mean, the real statement that I want is that, here's the real statement that I want. More than just net, even, or odd, what I want is something like n equals 2k plus 2 or n equals 2k plus 1, because I know that n is large enough. So maybe I should start with that. I have that there exists a k such that n equals 2k plus 2 or n equals 2k plus 1. Obtain from this that I want to use something like this I'm splitting up this here. And so this is what I have. So now I can just use this. This is now what I want. This is trivial. This is what I want. Now I use the transitivity statement here, and no goals to be solved. Because this is like it, so it works out just as well. So I'm sorry, just to reiterate what I've done here. Now I'm trying to prove, so down here, I was trying to prove that 2 to the 2k plus 1 is less than or equal to 2 to the k plus 1. And what I'm trying to do here is trying to prove that 2 to the 2k plus 2 is less than or equal to 2 to the k plus 1. Yeah, the only difference is that there's an additional additive factor of 1 here, but that only changes it by a factor of 2, and we already have like a factor of k to work with. And so I can just do the exact same thing, and now the linearith is happy to deal with the fact that 4 is less than or equal to 2 to the k plus 1, or 4 is less than or equal to 2 times k plus 1, and that all goes away. And so this is an independent fact, which is, I mean, this should really be dealt with by a simple MF, right? The fact is that LCM 0, 1, okay, well, it's not exactly equivalent, sorry. I was going to say that LCM is like strict mono, but it's not strict mono because 0 is equal to 1, as we had been talking about before. So lemma LCM LE LCM. So this is the fact, which should be easy to establish. And down here, we can just apply this fact and use linearith. And okay, so clearly, so what's the best way of proving this? Who knows? It'll be something like have I have this, or obtain HM from this. Cases HM with, yeah, okay. I'm just not gonna deal with this for now because like this seems, does grind deal with this? Yeah, because it's in exists, so it doesn't know how to deal with it. Yeah, so either this is the case or this is the case. Okay, I'm just gonna leave this. Let's see. Maybe you just want to extract the lemma for odd numbers and then use that for the full theorem. Which lemma? This is what I did here. Maybe there's like a stream delay. I assume that this is what the commenter is talking about. LCM, LCM. Oh, you can conclude that from that LE of David. Ah, yes. Okay, maybe you're talking about a different lemma. Yes, right. Yeah. So apply. Yeah. So I've already established this. This is for other numbers. Yeah. Okay. I mean, have I already established? So I guess yeah. So one proof technique here would be to say I'm going to apply the fact that this is less than this. I'm going to apply nat.le of David. And now I simply have to prove this is true and this is true. Because so basically what I need now is like a further lemma, which is LCM David LCM, which would be something like David. Right? This is also true. And in fact, this a David, so this would in fact be an easier way maybe of proving this. Okay, so sorry. So yeah, maybe there's a way we can like rearrange all of this to be a little bit yeah, sure. The point is that I can actually prove this statement, which is that LCMA, the LCM of the first A numbers divides the LCM of B as long as A is less than or equal to B. So this is a fact that I can prove, and I should actually be able to prove David LCM directly from this, because I should be able to prove something like, okay, A divides LCM A, that's trivial, and therefore transitivity of divisibility. Yeah. Unfortunate stream delay, but yeah, and I'm on like there's no way to get it better because it's just like ultra low latency. Maybe the nature of the stream delay is it doesn't like it's hard for me to like see. It's not like very visually apparent when a new comment is made, so I don't always see it immediately. Okay, so yeah, so what am I doing? Let me see. Okay, so this theorem is stronger, it feels, than the David LCM theorem, but probably can also be proved by induction. So yeah, nat LE induction. That would seem right. Yeah, like in some sense, it's always good to decompose the LE into like A is equal to B plus something, or A plus something equals B. This is a right. So induction. Yeah, right. What is the type signature? Using LE induction, not dot LE induction. Right. And so do I have to do B comma HAB? Is that the syntax? Is it explicit pattern match? Yeah, okay, cool. So I seem to have succeeded there. This should not be too hard. Exact and successor, right. Clearly I need like inductive hypothesis statement here. And so I have LCMA divide. So this feels like a great instance to use transitivity, because now I'm just using the transitivity with LCM. Sorry, yeah. In fact, this is a better yeah, straight use the induction tactic on HAB. Does that work? Induction HAB. What changed? REFL has not been specified. Okay, so wait, how does it want me to write this? Click on the light bulb. Okay, so it looks slightly different. Interesting. Is there a way of seeing what the induction principle it is that I used, what the name of that is? NLEN. So clearly this is still exact. And step. So step NM. NLEM sucks. So this is HLE maybe. I feel like I need an additional variable here. I have a free variable, or a variable without a name. Foo bar. Let me see. Is this too many variable names? I think that Yeah, okay, well, this is a little dumb, but it should be like something like this, maybe. Something foo or without this? Yeah, okay, so this should be HLE. Yeah, this is very similar to what I had before, I think. I think I'm probably just going to go back to the LE induction because I'm not like experiencing good names for everything here, right? So this is just what I have. And the point is that there can be something even better, which is lemma, LCM, divid, LCM, suck like this. For any m, this is true, and that is the proof. And now this, and now exact LE trans of HM of what is it? IH this. Did I get something wrong here? Apply. What's going on? Could not unify the type. What I wanted to do is that, sorry, divid trans clearly is the issue. And this is exact something. Great, cool, that's great. Show term. Great, wonderful. Okay, so this is this. Okay, so I proceeded to prove this. Divid LCM. Right. And now, okay, so the point is that now that I've proven this, proving everything else should be much easier. So number one, the reason this is true is, okay, exact. I mean, this is because, so sorry, just a sec here. This can be a sorry. This should be an exact because I already just proved this. And I need some like sort of edge case constraint. Oh, apparently I need positivity. So LCM lemma LCM pause. LCM lemma LCM pause. By cases simp LCM. And can positivity handle this? Positivity. Yeah, wonderful. So that's great. Positivity. Oh, that's interesting. Why did this? Ah, it's because we don't actually have the so I should like use my newfound metaprogramming skills. So like this is my metaprogramming skills in action. I have this. I just proved that the positivity. So this is going to be eval LCM, a positivity extension for LCM. It's going to take arguments of the form LCM nat.lc. Is this should really be in the nat namespace. Nat.lcm. It takes one argument. Nat.lcm of one argument, and it should be nat.lcm pause, something like this. And now positivity works, great. Okay, and I think part of the whole argument here is that we can now, okay, correct me if I'm wrong, but I think we can now just do transitivity with LCMA. The first is dealt with by, just a sec. A divides A dot LCM. Right. This is maybe another, yeah, okay. This is just another thing that I can write. This is maybe vid LCM. I'm just going to do one argument. The point is that A divides LCMA. Or by, yeah, for A greater than 1, sorry. HA 1 A. Right, really this should be cases A. I don't need that. Yeah, I don't need it to be induction anymore. Okay, great. So this is yet another lemma that we provided. And now the point is that this is dealt with by an exact, probably. Yeah, sorry. Divid LCM of LE maybe. And these are both exacts. Great. And I probably, okay, so I can delete all of this. I can probably just do something like show term to get this. What is this? Oh, this is like a tactic. Divid trans maybe. Yeah, that's much better. Okay, wonderful. Lots of golfing has been done, and probably I should correct the tactic I renamed. So this is now called this. All right, that was fun. I think for the sake of the positivity tactic, it would be nice if the assumptions are 0 less than A rather than 1 less than or equal to A. Yeah, is that a technique that people often use? because it is true. Yeah, this is sort of why the convention is to write positivity in that way. So yeah, let me make sure. So let me like search my entire file um, for things of this form. Copy line. So I have like 12 instances, and probably I should just never have this. Yeah. Okay. So let me do magical find and replace. I just want to replace 1 less than or equal with 0 less than. Replace all in file. And then I go and correct the errors. Okay, this is positivity maybe. Does positivity work now? Yeah, great. So this is like a great way of like using positivity better. And it looks like I don't have any more errors in this thing. Although I did put too many spaces, so I'm just going to delete those spaces. Great. Yeah. Okay. So what's next? Okay, so I proved all this. This is just some sort of divisibility thing. Right, this is the like, okay, so I sort of view this as the key step. And I guess there's one more thing, like LE9, or this is like 9 LE, but it's possible to get it down to 7 LE by explicit casework. The point is that it's actually true for 7, I think. I do like by cases, and by cases 9, or not, yeah, sorry, that's what I wanted. 9, LE, N. Otherwise, and the point is that in this case, I can do interval cases N, and then, so this reduces me to 2 cases, and in this case, I can decide or something. Basically, like this is a symbol to indicate that I'm doing heavy computation here, but yeah, so this is how one reduces. This just like explicitly evaluates. Yeah, okay. Probably using tons of compute to do that, but whatever. Okay, but I feel like this lemma is sort of the heart and soul of what's going on, so I sort of want to prove this. So the point is, I have that 2n plus 1. So this follows from. Okay, so first of all, I have h1, which is just this statement for n times n choose prime n of n plus n dot LCM. Yeah, LCM 2n plus 1. Okay, so the way that I prove this is using this statement. So I think what I do here is I have h2 prime is equal to, calling this with n plus 1, I believe. So that does that. No, something's not right. No, yeah, this is right. And the point is that I use this, right? M plus 1 times 2m plus 1, choose m plus 1, is equal to, yeah. This is just sort of like a silly lemma. It's like, I don't even know like what the right way. Should I inline it? Should I not inline it? The point is that there's a lemma which says that probably, I wonder if this, so this is basically the point is for any natural, it's going to be the case that, okay, let me write it in terms of choose prime. That dot choose prime of m plus 1 m is equal to 2 times this. And what's the intuitive reason for why this is true? So clearly this is like 1 off from a central binomial coefficient, right? And the ratio is this. I mean, I guess there's no like real good way of looking at the Pascal's triangle and understanding why that's true. But I think the point is that we break it down into factorials. Yeah, okay. Proof by factorial decomposition. Sorry. So I think the point is just that this is a true theorem. And what we do here is we have this statement. Now I just like rewrite exact. Or wait, what have I done wrong? H2, exact H2. What did I do wrong? What's going on? N plus 1 plus n. Convert H2. Let's see. I have more comments. I think for the sake of positivity. Yeah, no. For golfing, you can also delete the by and exact. Do I have a by exact somewhere? Oh, maybe I already got to it. Exact. This can just be deleted, something like this. Oh no, the conversion didn't work. Why didn't the conversion work here? One is that these two expressions are nearly identical. When I try to convert, how does that happen? Using one? Ah, the problem is that it goes too far. It's always so hard to using two. And now this is norm num. Or no, sorry, like ring. Ring is what. Sorry, maybe the point is that I should have just used ring and f, and that would have been correct from the start. But yeah, I was doing. I said norm num at some point, and that was not the right tactic to use. Okay, but that's how that step works. And the point is that from h1 and h2, this is true. And this is some theorem like, yeah, I'm tempted to do something like, so the point is actually that there's a one that I'm missing. Have h1 prime, right? The point is that it divides this, so it also divides this. It would just be easier if I did ring nf at h1. Oh, that's a little awkward. Yeah, that's a little ring nf. It, could ring nf be made to output the two on the right hand side or on the left hand side? It's so much more typical to see like the coefficient on the left hand side. I wonder why this happens this way. Yeah. I saw at least two bi-exact pairs. They're separated by a new line. Okay, clearly, yeah, bi-exact. You can search with a regex. Yeah, so clearly I don't want to do that there. Yeah, so if I wanted to like search by regex, I turn on regex by new line, and then some number of spaces, which I guess is s. Exact. Wonderful. So this can go away. Ooh, 100 character limit. Oh no. Yeah, that's right. And then this is also another example. And I guess I have one here too. Yes, getting rid of the by exact pattern. Great. But that seems to be the only remaining ones. So. All right. Well, I'm coming up on 2 hours, so I probably don't want to go too much longer. But let's see if I can try and like finish the main parts of this proof. So the point here is that this was a example of, yeah. So this is an example of transitivity. LCM2n. Yeah, the interesting thing is, yeah, so convert h1, and this is, so I want to do like using 3 or something, maybe 2 ring. And then this is apply. Shouldn't this be an application of the suck lemma? Yeah, great. So that deals with that. So I have basically the point is I have this, and now I'm here at h3. And the point is like I can even like replace this. I could say like replace. And so I have n times n choose n divides this. And I have 2n plus 1 times this divides this. And there should be some way, like clearly the other thing that I need is that n is co-primed at 2n plus 1. Right. The thing is, I don't know if there's going to be a lemma in this in MATLAB about this, because the point is that I can divide off n choose n from this value, and I have two things that divide the same value, and they're co-primed, therefore their product divides that value, and therefore rewriting it. Yeah, so this is just like a, yeah, I don't want to mess up the edge cases around 0 here, but the point is that I have like mul divid. Mul divid. Point is if I have A, B, and C, they are knots, and HAB says that A dot co-prime B, and we also have, yeah, HA. This is a little unfortunate. It's going to be something like this. This is it's definitely like not a good MATLAB lemma. The thing is that A HAB. Oh shoot! I lost my my window here. Yeah, sorry. Returning over here. Yeah. Okay. Sorry to fix that. It's like HACD is going to be something like A times C divides D. B times C divides D, then this happens to be true. And this is the theorem. I obtain this, I obtain this. I'm tempted to like substitute one of them, like subst hy And I guess the point is that obst y, rewrite hx. Yeah, so yeah, okay. Um, yeah, I'm losing the plot here. The right. So thinking about what I want to use here, right? So I have a times c is d, right? The point is that d divided by c is a multiple of a and b. So the quantity is going to be like, ooh, am I going to have to like do divide? It's like LCM a b, or it's probably like LCM a b, right? No. Ugh, okay, yeah. Sorry. The point is, x is d over ac, y is d over bc. So what I want is d over abc. So I'm gonna have to like divide off d or something. There should be a way. Okay, yeah, and probably I'm missing some statement about how all of these have to be greater than one, or non-negative or something like a pause, b pause, c pause, d pause. Great. So a bunch of those things which I can remove later if I don't need them. And there should be some way, right? Like I feel that when this happens, when the entire goal is just like saying that things are co-prime to each other, it's all multiplicative. All the statements in this goal are multiplicative. And so really what this comes down to is like there should be some tactic that my point is that there should be some tactic that deals with goal states like this, because it's really just a matter of checking for every prime factor. Right. You could consider the prime factorizations of each of these things, right, as functions from the set of primes to the number of factors there. Um, and then proving this is just a statement about like particular multisets and how some sum to another. And you can maybe like verify it by asserting for every prime that this is the case. But I'm sort of flagging here, so I'm probably going to turn off the stream right now.